So today I'm going to teach you guys how to understand parametric equations and how to graph them. So they're pretty simple. It's simply a fancy way of saying x and y as functions of time. So I'll write that down. Oops. What did it? I think it's still going. It says it's still going. So let's say we have our graph here. Oh, do you want me to stop this? Okay. And let's say we have a cliff that's approximately 10 meters out and approximately 50 meters high. And we have a car on the top of our cliff. And this car is going off the cliff at about 5 meters per second. And we want to find the path in which this car is going to fall off the cliff. And we'll draw some water so we can talk about the demise of the car. So what we're going to have is we're going to have two functions that are going to help us show our path of the car falling into the water. And they're both going to be in relation to time. So we have our xt. And how we create our xt is we have our distance times our velocity. Our velocity is 5 meters per second. So we have 5 times t. Then we have our starting point on the x coordinate, which is 10. So we do plus 10. And then we have our y in relation to time. And how we create the y is we have our starting position in meters in the air, which is our 50, since the car is on the cliff. And we do not have a y velocity, so we do not add that. But what we do have is we do have gravity that is pulling this car down, but we're not considering any of the Newton's laws or anything. This is technically a scenario in a vacuum. So we have approximately -10 because the car is falling down in relation to gravity. And then we have t squared divided by 2, which could be simplified to -5, but I'll just leave it as it is. So if we want to track the path of this car as it falls to its demise, we get to create a graph of t, of x, and of y using the graphs that we have. So let's just do some random t values. We have 1, 2, and 3. And then our starting position, of course. And at t of 0, we have our car on top of the cliff, where x would be 10 and y would be 50. Now, if we plug t into x, it gives us 15. And if we plug 1 is t into y, that gives us 45. Now, if we go to 2, t equals 2, we plug that into x, and we get 20. And we plug t equals 2 into y, we get 30. And now for time equals 3, we plug 3 into x. That gives us 25. And we plug t of 3 into y, and that gives us 5. So now we can kind of see a pattern with the x. It makes sense because it's simply moving 5 meters per second to the right, like our graph is doing. But y is a bit more dynamic because it takes into account the fall, acceleration, etc. So now what we want to do is we want to plot these. So we have t equals 0, which is right here. T equals 0. Beautiful. And then we have t equals 1, which is at 15. Let's do that. 10, 15, 20, 25. And then we have 10, 20, 30, 40. And so at t equals 1, x is 15, y is 45. So right under here, this would be our t equals 1. We have t equals 2 at 20 and 30. Yep, 20, 30. And then t equals 3 is at 25, 5. So now this, we can see, is the path the car is going to take as it falls off the cliff. And we can assume that in this little space right here, t equals 3 point something, something, something is when the car will actually intersect the axis and fall into the water. So considering this, we can now calculate what time the car would be at any time of t in this sense. And that's the great thing about parametric equations is we can assume a third variable using x and y instead of just having a plain x and y coordinate. Nonetheless, we can also calculate the direction based on where our t0 to t1 to t2 to 3 to t3 goes. And since we have a scenario of a car falling off a cliff, we know which direction it's going, and it's going down. But with more complex equations, it obviously gets a little bit more difficult to calculate the direction. But we know the car is falling down. So that's the basics of parametric equations. I hope it helped you learn something.